In the quantum mechanical model, we describe these orbitals of the electrons and atoms using what's called a wave function. We use the Greek letter psi to represent the wave function. The wave function is calculated using an equation h psi equals E psi. The H is a operator called a Hamiltonian operator. So we put in the constraints into the equation, and the solutions is when this Hamiltonian operator operating on the wave function psi gives us a eigenvalue of energy. So it will be energy times the wave function. So in our Hamiltonian, we build in the constraints of the size of the nucleus, how many electrons present, and this equation gives us out the energy of the various orbitals of the electrons that are allowed for that particular atom. So the wave function psi doesn't directly correspond to a physical object, but what we get is by squaring the wave function psi squared, the value of that will give us the density or probability of finding an electron within a location of space. So psi squared is our probability density, probability of finding an electron, or electron density of the electron around that atom or in that orbital. So psi squared is giving us the shape of the orbital and the electron density or probability of finding the electron within that orbital. We have 4 quantum numbers that we use to describe our electrons. The principal quantum number, we use the letter N to represent this. This is the principal energy level. For the hydrogen atom, this is the only number that we need to determine the energy level. For multi-electron atoms, we need additional quantum numbers to describe the energy levels. So the principal quantum number N consists of counting numbers. 1, 2, 3, 4. So the integers, there's no zero, there's no negatives, just counting numbers. 1, 2, 3, 4, 5, 6, 7. And there's no limit to this value also. So even in the hydrogen atom that has 1 electron, all these principal quantum numbers are possible. They become a reality when the electron occupies that level, and their potentiality at all times. The next property is the angular momentum quantum number. So the electron is spinning around the atom. There's different ways it can spin around the atom, and because of those different ways it can spin around the atom, it creates different types of angular momentum. So we're going to use the letter L to represent angular momentum. It has values from 0 to n minus 1 for each value of n. So if n equals 1, it's going to have the value of 0. If n equals 2, then L can be 0 or 1. 2 minus 1 is 1. So the number of L values is always going to equal the number n. But it starts counting from 0, so the value of L will always stop 1 integer less than n. The values of L correspond to the sublevels in our electronic structure. we see 4 sublevels of ground state electrons in our periodic table. We call those sublevels SPDF. So S occurs for n equals 1. That means S equals L equals 0. So the angular momentum quantum numbers map onto specific sublevels. So L equals 0 is sublevel S. L equals 1 is sublevel P. L equals 2 is sublevel D. L equals 3 is sublevel F. We have more sublevels. The SPDF originally came from spectroscopy. They're referring to sharp, principal, diffuse, and fine. We don't worry about the names anymore. And after F, we would just start to count alphabetically to represent the additional sublevels. The next quantum number represents the magnetic quantum number. We use M sub L to represent the magnetic quantum number. The magnetic quantum number is going to correspond to specific orbitals. Specific orbitals are going to be specific shapes of the electrons that contain 1 or 2 electrons. The value of the M sub L is going to range from L to negative L, or negative L to L. It has integer values. So it starts at negative L, we add 1, add 1, add 1 until we get up to L. What this gives for us is that we're going to be adding 2 orbitals each time we go up in L, each time we go up to the next sublevel. So sublevel S, L equals 0, has a magnetic quantum number of only 0. No other values allowed. Which means that there's only 1 orbital in the S sublevel. For P, the value of L equals 1, so we're going to go -1, 0, 1. So we have 3 orbitals. We increased it by 2 orbitals. For D, L equals 2, we're going to go -2, -1, 0, 1, 2. So we're going to have 5 orbitals for D. So we went from 3 for P to 5 for D. We increased it by 2. For F, L equals 3, so we're going to have -3, -2, -1, 0, 1, 2, 3, a total of 7 orbitals. D had 5, F has 7, we increased it by 2. So we're increasing it by 2 each time. Now the ML numbers, we do not have a direct map of ML onto the other designations that we can use for these orbitals. For P, since there's only 3 orbitals and they are orthogonal or perpendicular to each other, we line them up to a Cartesian coordinate system and call it Px, Py, Pz. We do not specify that one of these is -1, one is 0, and the other one is +1. The last quantum number that we have is the electron spin quantum number. Let's see, the magnetic quantum number. This is representing the orientation of the orbitals in space. So the azimuthal quantum number, the angular momentum quantum number, is representing the shape of the orbitals. S is spherical, P is 2-lobed, D is 4-lobed, F is 8-lobed. Magnetic quantum number represents the orientation of these lobes in space. And then electron spin quantum number. We use m sub s to represent electron spin. And electron is spinning, or it behaves as if it's spinning, a spinning electrical charge. Spinning electrical charge creates a magnetic moment. When we put it into a magnetic field, it can line up with or against the magnetic field. That's the plus or minus aspect. The 1/2 represents rotational symmetry of the particles. All matter particles have a fractional rotational symmetry. So a rotational symmetry of 1/2 represents that the electron has to do a 720 rotation, 720 degree rotation, so 2 full rotations before it appears like itself. So it appears to the way it began. And the electron spin in the orbital here, we're allowed to only have 2 electrons in this orbital. Those 2 electrons have to have different spins. So for each orbital, we can have a spin up and a spin down electron. So we have a plus 1/2, minus 1/2. We tend to call that spin up and spin down. So for each orbital, we have a spin up and a spin down electron. So we have a maximum of 2 electrons per orbital. So some numbers. Let's see here. Each shell will have n subshells. So shell 4 have 4 subshells, SPDF. Each subshell will have 2L plus 1 orbitals. But since L is 0 for S, that means S is 1 orbital. L equals 1 for P, so that would be 3 orbitals for P. L equals 2 for D, that gives us 5 orbitals for D. L equals 3 for F, which gives us 7 orbitals for F. The total number of orbitals in a shell will be n squared. And since there are 2 electrons per orbital, each shell will have 2 times n squared electrons.